Hello, welcome to our first lesson on Kirchhoff's laws. Now you may be wondering why we are not going through your test that you did yesterday. As you can imagine, with everyone handing it in by the end of yesterday, there wasn't really time to mark it for this morning. So instead, I will go through it next lesson, which I'm afraid will be next week. So yes, today we are looking at Kirchhoff's laws. Now we're still doing electricity, but we've now moved on, I think it's to chapter 10. And for the last two chapters were chapter 8 and 9. This is now going on to chapter 10. And it's a way of thinking. Series and parallel circuits that you did in GCSE, we gave you really simplified rules for working out the current and the voltage. Now you'll be given questions in A-level, which the simpler ones look like the GCSE ones, and you might be thinking, why can't I just use the series and parallel rules? But the harder questions will rely on these laws. So those rules were basically, as I say, simplified versions of these laws. And yeah, basically you need to memorize these so that you can then apply them to different situations. If GCSE is fact recall, current is the same everywhere in a series circuit, A-level is the application of that knowledge. So yes, Kirchhoff's first law, it's all about current. Total current entering a junction equals the total current leaving a junction. And here you've got total current in equals total current out. Yes, so that actually applies, if you think about it, to series circuits, because in series circuits, I'm just going to draw on this. Oh no, my Apple Pencil's going to die. I feel like in every video my Apple Pencil's about to die. I'm not very good at charging it. Can I draw with my finger? No, I can't. That was a bad idea. Let's get rid of that. Okay, right, let's try again. So, in a series circuit, fine, you've got your power source, you've got maybe a bulb, maybe we'll have a thermistor just to make it exotic. As you can see, there are no junctions in this series circuit. So everywhere, there's nowhere for the current to leave, which means the current has to be the same everywhere. So that rule has actually told us that. No junctions, no splitting of current. However, in a parallel circuit, you've got a junction here and a junction there. Now here, and that is quite important, let's say this is I1, current 1 coming into the circuit. That means current 2 might be going down here, and current 3 going across there. So I1 is going in, that is your total current in, and that has got to equal the total current out, which is made up of I2 and I3. Do you see what I mean? Because at that junction, you've got a certain amount going in, a certain amount going out. And the same applies for the junction on the other side. So that's Kirchhoff's first law. Second law, the total EMF around a series circuit equal the total potential difference across each component. Now, I've put it slightly differently here. You can see again that's that total, that little E is EMF if you remember, V is potential difference, and it says around a closed loop. Now that loop, that idea of a loop is very, very important. We're going to spend quite a lot of time practicing this one because it's all about getting you used to spotting loops in circuits. But from that you can basically figure out that in series the potential difference is split, but in parallel, in fact, I'll draw a parallel circuit. Excuse me, sorry, I'm hiccuping away here. Okay, right, so let's say you have 10 volts of EMF in at your power source. Then I did not mean to do that. I'm such an old person when it comes to technology. What was I trying to do? I was trying to draw. Here we go, that's what I was trying to do. Okay, so a loop. That is one loop. The 10 volts of EMF must be 10 volts of potential difference in going into that bulb. But look, there's another loop that you could draw. The other loop is around here. Do you see what I mean by a loop? Goes from the circuit, from the battery to the thermistor and back. And again, total EMF and potential difference have to be the same. So 10 volts of EMF, got to have 10 volts of potential difference here. Do you see? That's told us that in a parallel circuit, the potential difference is the same. Right, we're going to do lots of practice questions on this, so I shall see you on Zoom. Bye!